APIs that we have currently. We split them roughly into groups. The grouping sometimes works, doesn't always work exactly, but it gives you kind of an indication. There's a bunch of 3D APIs. The exception is OpenVG, which is a 2D API. OpenGL, OpenGL-ES, OpenGL SC, safety critical for those kind of in automotive and avionics, but the main focus obviously is on Vulkan that we've had today. The parallel computation at the bottom, OpenCL, OpenGL for graphics, OpenCL for compute. So a general purpose compute API lets you use all of the compute resources in your system. SPEAR-V, as you saw about it today, is kind of a fundamental part of the Khronos ecosystem. SYCL is something slightly different. It's a bit like CUDA. It's single source C++ programming for parallel computation. Then on the left-hand side, we have some vision and neural net related stuff. OpenVX is much higher level than OpenCL. It's basically a directed graph that lets you describe Lego blocks for vision processing. So an implementer can very efficiently accelerate it on any kind of processor or architecture that they have. A couple new initiatives. We don't have logos yet. Neural Network Exchange Format, we call it NEF, is like, well, Peter, the working group chair, so like PDF, but for neural nets. You've trained a neural net, and you want to get it down into real-time inferencing engines. It's a way of encapsulating the training that's gone into a neural network. And VR initiative, we don't even have a name for that one yet, but it is the VR industry coming together to create a set of APIs for portable VR. And last but not least, up at the top, the web-related stuff, WebGL, probably familiar to quite a few people here, bringing OpenGL-ES capability into the browser. We're just about to formally release WebGL 2. GLTF is a 3D asset transmission format. It's kind of like JPEG for 3D. And Collada, which is an authoring format that was created some time ago. So if you wanted to get involved in Khronos, you have a number of options, and it's kind of increasing commitment going from right to left. So as Tom has mentioned earlier, all the specifications, a lot of the conformance tests, a lot of the samples and tools that we're working on for Vulkan and the other APIs are in open source, and that's a trend we're trying to accelerate, putting as much as we can into open source on GitHub. So you're always welcome to come and help us fix and evolve stuff in the open source ecosystem. If you want to get a little bit more involved, there's the option to either join or even run a Khronos chapter. Khronos chapters are like meetup groups, but Khronos will help with beer and pizza money and content, in some cases speakers. We try to get speakers into the right place at the right time, so meetup groups can really engage with the Khronos ecosystem at a grassroots level. We have around 20 active chapters around the world, so go onto the website. If where you live doesn't have one, please feel free to start one, and we'd love to talk to you about that. The third one along is actually interesting. It might affect some people here in a good way. We have something called the Vulkan Advisory Panel, which is people that aren't quite committed enough to join the Khronos as a Khronos member, but they have enough skills and feedback to really advise the Vulkan working group what we should be doing and provide requirements and ideas on how Vulkan should be evolving. The way it works is that there's no fee. And if you talk to us and we think you can indeed add value, we'd be glad to invite you onto the advisory panel. You sign the same IP framework and NDA agreement that the rest of the Khronos members have signed, but there's no fee. So we can, because you're under the same IP framework, we can actually send you draft specifications before they're public and get your input on key design issues as they come up in the development of the specification. And we can take that feedback and build it in to future versions of the spec. If that is something that sounds interesting to you, being able to influence how Vulkan evolves, please talk to any of the people here, and we'll be glad to give you more details on that. And then last but not least, of course, you can become a Khronos member. Yeah. You can become a Khronos member. So it's open to anyone. For smaller companies, there is a membership fee, but it starts at 3,800. It kind of goes up from there, depending on the level of participation and the size of your company. But we do try to keep things accessible. Again, people actually helping and contributing is the lifeblood of what we do. And then, last but not least, GDC. So the next event after this one is Game Developer Conference in San Francisco. How many people are going to GDC? Yeah, okay, there's quite a few. So there's this is what we're doing. This is actually our internal planning slide, but I threw it up anyway. So the Vulkan Advisory Panel is actually meeting face-to-face on the Sunday. And that's the first time we've actually met face-to-face. Up to now, it's been electronic, but we want to deepen the interaction with the advisory panel folks. VRDC is the virtual reality precursor to GDC. That's happening on the Monday and the Tuesday. We have a table, and so come and talk to us. We're going to be talking particularly about the VR initiative. We have a developer day on Tuesday, so all the way through Tuesday there'll be Vulkan-related sessions. There's sessions on the web, WebGL and other web initiatives, Vulkan, of course, the VR initiative. So we're on the program, so please come along to that. And then during GDC itself, Wednesday through Friday, we have a booth. And so you have questions. We're going to make sure that there's people there throughout the 3 days to answer any questions or ideas that you may have. And last but not least, on the Thursday evening, it's always a fun event, is the WebGL meetup. It's a couple of local chapters. We're working with them to do a cool meetup. That's actually going to be the official launch party for WebGL 2.0. There's a bunch of stuff happening in GLTF as well, so be there or be square. So that was any questions on Khronos in general? So let's get into the panel. So we want this to be your questions, not our questions. So please feel free to ask anything. Can be related to Vulkan or anything about Khronos. We have combined skills to cover pretty much any topic here, I think. So any questions so far? No, yes, go ahead, Angelo.
Yeah, this is kind of more of a general question, but like you mentioned that you're being more involved with the open source community and you've been pushing code onto GitHub and accepting, I don't know, maybe accepting pull requests or accepting bug fixes and such. Now, kind of like the obvious elephant in the room is that Microsoft these days has been doing the same. For example, in opening up fairly recently, like their new HLSL compiler, which generates like DXIL, bytecode, and such, and of course across like other technologies as well outside of graphics. Are you guys looking at all to like maybe having a look at their code, since it's freely licensed as well, to like kind of improve maybe your tools in that regard?
Yeah, that's a great question. We were just talking about that.
Yeah, we're going to look at the front end there. Obviously, if we started using that code base, it would be a delay in where we're already at with HLSL. So in the very near term, we'll follow through on the HLSL that we have. Now, if we start getting into DX12 or C++ features where the trade-off is leveraging their front end versus writing our own C++, at that point it makes more sense to switch to leveraging their front end. And there are two choices there. One is the ideal way is to leverage just the front end, not the LLVM part, but accepting or reusing their parsing of the language, which builds an AST. SpearV generation today with GL slang translates an AST to SpearV, and we make the same AST from both GLSL and HLSL, so we get to leverage that translator. But if we leverage Microsoft's recent contribution, we'd probably start with from the C++ source code down to their AST and then translate the AST to SpearV.
Thank you.
And the timing of that, well, like I said, it'll depend on like once there's strong need for things where it's faster to get it that way than the other way, we'll switch over.
Would people like to use HLSL with Vulkan? Who would like to use HLSL with Vulkan? Yeah, a lot. Yeah.
I want to plead guilty here because I was chair of the OpenGLES group for years, and we debated periodically, should we do a device-independent binary or device-independent low-level format similar, well, not similar to shader model bytecodes because they actually suck. They are terrible. But I just resisted and dug in my heels and dragged my feet forever. And when they took me out in the back alley and put a bag over my head and it made me submit. It's the best move we ever made with SPIR-V. It's so fantastic because there was zero value in every vendor having a slightly different parser for OpenGLES, for GLSL-ES. So very excited about this trend and very glad that I saw the light finally.
Another question, I'm actually interested, who would be interested to use C++ as a shading language? Not so many. Interesting. So HLSL is the sweet spot.
What if it was in line with the rest of your source code? How about then? No? How more interested would you be in C++ if it was just written in line with the rest of your source code?
I think that's a bad idea. It's a panel, right? I can say stuff like that.
It's more
No,
interesting.
the thing is, I mean, a game is a piece of content played by an engine, right? The engine is the player, and the shaders are part of the assets, and you don't want them in the source code. You want them in the distribution package, surely. Am I right?
There's a question here.
Sorry to kind of expand on that a bit. I mean, Microsoft have AMP, which is kind of that, and I'm not sure many people are actually using it. But maybe I'm not the standard audience for it. My other thing on that would be, there is, things like compute shaders and just basically maths kernels would be quite useful to be expressed in C++, so we could then offload them. I think there would be some use to that. But from a pixels on the screen point of view, I can't really see it.
That's interesting. There's a latency. Right.
In the OpenCL side, but it's definitely more compute, not anything to do with graphics, so it is different. The trend is towards C++ single source, I think, for many people.
I was waiting for it to light up green, just so I didn't do what Tom did. So I think I think for most of the people that I work with, the biggest thing that C++ would bring would be syntax highlighting that actually works.
At a language level, there's more to it than the syntax highlighting.
Not to get into a debate, I really was trying to make the point that I do think that on the language side of it, though, for authoring, the tools are really important, and I almost always have to fight with editors that think they might understand my shading language but don't quite.
Right, but I think the point is both OpenCL and HLSL are rapidly picking up C++ features in their high-level languages, and Khronos will be translating those to SPIR-V and using them as SPIR-V. So there's a long-term vector of doing that, and so that's the direction things are going.
And I think a higher level point here is that as a driver implementer, I don't really care. Use whatever language you want, write in SPIR-V. The beauty of SPIR-V is that we're completely immune to whatever crazy language choices you make by design. That's the primary goal of SPIR-V, to remove ambiguity in the driver implementation. So go forth and create languages. Go translate Java to shaders. We don't care.
I think people really like that idea.
Yeah, we'll try to keep the mic in the hands of the people who know what they're talking about.
So not that I want this to be a competition between DX12 and Vulkan, but I understand DX12 more. So maybe if there's people on the panel that also know what's out in DX12, I'm wondering if you could explain any differences between the APIs you think are important, like, hey, this is a great advantage for one or the other.
I don't know why you keep turning it off. Just leave it on. So there's two obvious ones that I always point out. The first one is that a pipeline cache in DX12 is not a pipeline cache in Vulkan. They're different things. In DX12, it's purely for serialization. It's, you dump your pipeline in there, and then you can write it out to disk, and you can load it back in later. Vulkan's does that as well, but it amortizes the cost of multiple pipeline compilation and will also serialize multiple pipelines at once. The idea is that I think we talked about it today during the talks, that the idea is that if there's common stuff being done between multiple pipelines, it will just be cached into the pipeline cache. And then at the end of all your pipeline compilation, you can just write that out to disk, and you can read it back in the next time, and it will drastically speed this up. I know at least during the SIGGRAPH talks, I think, probably id and possibly Epic did some talking about their use of pipeline caches and how much of a speed up they got. So that will give you some information if you're looking for it. The other one, which is one we've talked about a few times today, but not in any great details, render passes. Part of the reason we haven't talked about them in great details is because we've talked about them to death. So again, if you go have a look for other literature, but the main takeaway is what I said. It's basically a dependency diagram between various bits of drawing that you might be doing in your scene, with particular relevance on mobile, where you're expecting certain things to remain on chip, which you wouldn't otherwise if you didn't have that.
So I guess that's mainly an advantage to tile-based GPUs?
Yes, but not only to tile-based GPUs.
So just to iterate through a few more kind of high-level differences between DX12 and Vulkan, the binding model is mostly similar, but superficially different, such that you can implement a DX12 binding model on top of the Vulkan, and it's slightly more difficult to do that the other way, but they're still more similar to each other than, say, Vulkan is to OpenGL. So that's the other big difference you'll notice. And then Vulkan doesn't expose a few of the kind of what appear to be higher-level constructs that DX12 exposes, but that's not actually DX12, that's the DX12 runtime, which Vulkan will be implementing as, or potentially implementing as, open source libraries or layers. And then I guess the kind of biggest ticket difference between DX12 and Vulkan is the absolute insane multi-draw and direct code that DX12 exposes with the root table updates you can do between multi-draw calls. And there is nothing like that in Vulkan, and I would be surprised if we saw something like that in Vulkan soon.
That all that said, the similarities between Vulkan DX12, they are far more similar to each other than any of them are like DX11 or OpenGL. So we're pretty close together. I had another point. What was it?
But on that point, I think that's important, because there's actually no value in having different API. I mean, they're getting close enough that we should, at a high order, try to converge them rather than diverge.
I mean, there are, for example, if you're writing something and you want to run on Xbox One, well, you're going to have to write a DX12 backend. If you architect a good DX12 backend, porting it to Vulkan is not going to be a huge stretch, especially if you've thought about it a little bit beforehand. And it really comes down to a business decision of how do I most quickly amortize my development cost. And yeah, if console's important to you, well, I hate to admit it, but there's an obvious choice there.
Well, it depends on the console. Right?
Well, yes.
Nintendo is actually going to support Vulkan. So, I mean, that's the high order bit. Even higher order bit is the key difference, of course, is Vulkan is cross-platform. Now, not all platforms, of course, will decide to adopt it natively, but it is going to be available. And the fact that Nintendo are offering Vulkan as one of the APIs, I think is a good kind of indicator of the way things might go on other platforms too.
I want to piggyback on that question in terms of devices, and specifically to you, Cass, in terms of the Oculus. You have two versions. You have the mobile version, and you have the desktop version. How much standardization? I understand that you can share the source code, but where does that stop? And how is that affecting the business?
So if you're asking about sharing the source code for platform-specific implementation details, like the compositor, what's useful in the ATW samples that I talked about before is that it illustrates what we think is necessary for good VR, not necessarily what is complete. And from that perspective, we will expect that systems will have tightly integrated VR compositor subsystems, likely to be owned by the vendor of those systems. However, what isn't likely to be true going forward in the long term is that every vendor will have its own API, and that's what was the germ seed of the process of Khronos being involved with a VR standard API for developers. And I think that it is a surprisingly small surface area to provide a robust, solid application-facing interface for VR, and we should expect that will happen just because as the industry matures, it becomes clearer and clearer what that surface area looks like. And it's encouraging that I think a lot of people seem to think that's a good idea, Oculus included. So I expect to see writing portable VR applications get easier and easier, and you shouldn't expect to need to support very many platforms. And we'll see how far down that path we can go, but not unlike Vulkan, I don't think Oculus sees the API that we provide as the secret sauce. Doing it well and making sure that there's a good description that all developers can understand about how to write good VR is a far higher order bit. And then on the compositor side of things, we will do some things that I think that we'll be able to do better than our competitors, and those are the kinds of things where we will try to innovate, and I presume other vendors will as well. Did I answer any of your questions? Okay.
So if you want to hear more of Cass, one of the sessions we have as part of the Developer Day at GDC is going to be about what are the limits of VR standardizations, as well as telling you kind of our thoughts as to what the direction is, also kind of how far can we go, given there's very different gameplay, there's things that you really will not actually be able to, standards won't be able to solve. But I think on the wider point of where Vulkan draws the line about standardization, the key thing that we try to do was having as much as possible, especially outside of Windows system integration, one path that works well across the board. And yes, implementations can expose vendor extensions, and you can optimize a bit more if you're desktop focused or for a specific vendor, but you can rely on there being a path in the middle that is going to give you good performance. And for Windows system integration in particular, that was kind of the dilemma, and we still always thinking, have we got it right? But for your frame loop, that you can have a very portable frame loop between platforms, but then all the other gunk of Windows system integration, we did not try and standardize between X and Android and Windows, and that's where the pain points really are.
That is something, you know, when I think about how this group has operated over the last couple of years, and we just had this screaming fight again last week. It's a huge challenge for us, but a huge value if we succeed. What we don't want to do is to get you in the position where you're a developer and I have to query and say, well, if it's an NVIDIA GPU, I'm going to factor my code this way. And if it's an AMD GPU, I'm going to factor my code that way. And there's no shared code between them, or not enough. So we try very hard to have it be possible, although you're not forced to do it, but we want it to be possible to write one code path that runs quite fast on pretty much anything, including tile-based renderers, which are unbelievably different from traditional direct renderers. I won't say we've succeeded 100%, but I'm pretty happy with where we are.
And to continue this never-ending thread, I think Tom's completely right when he says quite fast. So it's untrue that if you want to get absolutely the most out of the GPU, that you can write a single path and expect it to run the fastest on all of the GPUs. But I think the big difference between Vulkan and something like OpenGL or OpenGLES is because Vulkan is so much more open and it puts so much more onus on the application to make decisions, finding out those differences is a lot easier on Vulkan, and actually writing those code paths becomes a lot smaller because we're not hiding, so you're not making a change which causes the driver to fall onto a different heuristic path, and then because it's a Tuesday, it falls into yet another different heuristic path. We expose all our dirty secrets, and it's up to you to take advantage of those. So, yeah, don't let anyone tell you that you can't write vendor-specific code in Vulkan, but that vendor-specific code is a lot more obvious, and it's a lot easier to understand the code that you're actually writing.
And I think I'd like to say Vulkan has done a pretty incredible job of finding. I don't think there was an optimal path, but there was a lot of effort put into finding a really good one that takes the corners off of architectural advantage, and in a way that doesn't penalize any particular implementation. And I think that's going to be good for the whole industry.
And just two last points. In terms of the difference between GLES and GL, sometimes this is the way things have been done. That's what we've avoided. So therefore, if you're developing for mobile, you can start off working on desktop and then bring it over to mobile without the random things that are different for no apparent reason. And a plug for the back, if he's listening, hi from Cinder, from Google, that works on the Cinder project. Not just because he gave the most emphatic support to Windows System Integration, that's not the only reason, but gave a really nice talk at the last Khronos GDC session about just being able to port between platforms, and what used to be days or even weeks of pain were half an hour jobs, and that's what Vulkan's managed to deliver.
Thank you.
Yep.
So, question for you: if you look at how we went through DX12, it was quite hard to learn the new way of doing things in the API, like, for example, resource transitioning, et cetera, et cetera. And in your presentation, you mentioned things like, oh, you have to optimize the index buffer because OpenGLES did that behind you. So DirectX 12 basically came up with the concept of what good looks like, which is their mini engine. I'm not sure if you're familiar with it. I was just wondering if you guys have any plan to build a mini Vulkan engine of what good looks like in a slightly larger scale than just an example code?
Not specifically. The situation at the moment is that we have some samples, such as the DevU sample. Most of the vendors have something going on. I know at least NVIDIA and Imagination have, and I think ARM as well, have sort of mini engine implementations, or at least higher level abstractions over Vulkan of some form. We have yet to decide to standardize on any of those. Although maybe Neil might want to say something in a minute. But in terms of getting stuff out there, we are looking at the idea of maybe providing samples for how to do common but tricky looking tasks like memory allocation and choosing the right heap and some other bits and bobs that you might otherwise have no idea how to attack them.
That reminds me, we are very, very interested in hearing about points of pain. One we've heard consistently from developers is, I wake up on a new machine, I start querying the number of kinds of memory types and memory heaps available, and I have no idea what I'm going to get. And I write a code path that works on the machine I'm developing on, but I have no idea if it's robust to what I might find on a different machine. So it's really valuable to us to know that. And as Tobias said, the only answer we have for that right now is we're going to try to write a really good example of a robust heap chooser. And Hai's going to interrupt in a minute, so Angela, need to take Hai the microphone. But we want those other stories. So the points of pain, when you start doing stuff and you find something that's just freaking impossible to do, please tell us. And you can do it on GitHub, you can do it here, you can do it anywhere.
So do you think we should do something? Yeah, go ahead. Hi.
And if there were good defaults for some of the structures, it would be great as well. You know, in lieu of having a full mini engine like example. One of the confusing things that I get asked a lot and don't really have a good answer for are things like subpass self-dependencies. Like when are they appropriate, when are they not appropriate, what are good default values for those? And it would be awesome just to have like a Khronos approved example of like, hey, these are the things that you probably do 90% of the time, and here's how you would set up the subpass dependency if you even need one, and various things like that. And it goes in line with what you said, the tricky bits of Vulkan. That would be awesome.
Yeah, I mean, specifically for subpasses, there's at least two I'm aware of that are pretty standard, which is getting from, well, one of them I put on my slides, which was getting from presentable and back. That's pretty much every application in the entire world is doing that, as long as they're rendering to the screen. So that's probably something that should go up there. And then the other one being deferred rendering, which we've talked about before, getting stuff between a G buffer from one end to the other. There's probably others. It's very hard to say that there's any general set of defaults for pretty much everything. But certainly, yeah, I mean, if there's specific things, then we could look at doing samples for those.
Yeah, so the Vulkan C++ layer could adopt those default values if we would define them in our Vulkan spec. We didn't start yet, but yeah, if you have any suggestions for good default values for each and every struct, we can try to start to integrate them and see what we can do.
So one of the things that I'll mention, at least if you look at the ATW example, is while it was designed to be complete in a single source file, that also dramatically negatively affects its accessibility except by pinhole view. You know, you can look at a page of text, but there are probably 50 pages of text in the file. So for samples, it may well make sense to do something like have two source files, one that includes the stuff that you shouldn't pay attention to, and the other which does the bits that the sample is intended to illustrate. And that's the kind of thing, because Vulkan is such a verbose API, it probably is worthwhile to have either really clear guards around this is the important bit to look at, or to do it in a separate file where part is ignore this please.c.
Well, that sort of is an important point, actually. The reason Vulkan is so explicit is because we need all this information. In a lot of cases, there's no one sensible default for anything. There's a good chance that 95% of cases, certain parameters are going to be this one thing, but then in the extra 5%, you absolutely have to set it to the other thing. At least from the Vulkan C++ thing, I think the right thing to do in most cases would probably be to provide pre-filled out structures with specific names. So say this is the present subpass dependency and stuff like that, but that's my opinion.
I'm trying to get these guys to talk. You guys need to encourage them. But I'll hog the mic again. Just to mention that in the VR API, we have a helpers header, and it really is because we have plain structs as well without any, they're C-based, no defaults. We have headers functions that their job is to provide you some common filled out for this particular use. And I do think that's not part of the API proper, but useful and educational as well.
Hello? Yeah. So if we would add those reasonable defaults to the Vulkan spec, we could generate some constructor functions for each and everything. So for the C API, C++, Python, whatever we want to do. So maybe it makes sense to think about if there's a way to enhance the spec to give those defaults or have default constructors.
Sorry, this is the thing that I did at the last time we talked on a panel. No, so last time we were on a panel together, I stole the mic from him, so I thought I'd just do it again. The spec is, I don't think, the right place for that. I do think there is a place for it, but I think it's documentation that's extraneous to the spec. SDK, for instance, like these guys are providing. That's not to say you can't also put it in the C++ thing. I think that is a reasonable place to put it. I do, but I don't think that belongs in the Vulkan spec. It's more of a programmer guide thing.
Yeah, and I think it becomes, it's not so much the default creation. So if we just look at a really simple example.
Yeah.
Okay.
Nobody can hear you, Mike.
If only.
So if we just take a really example of, say, a VK sampler, there's like, what, 16 or maybe 20 samplers that anybody would reasonably use in the wild, and there's probably 4 or 5 which are default. But none of those 4 or 5 are actually the default. But perhaps if in a tool or in a document or an example we could say, this is a pretty reasonable default for doing point sampling. This is a pretty reasonable default for doing shadow map sampling. This is a pretty reasonable default for doing cube map sampling. So there is no one default, but a small number of defaults does cover the vast, vast majority of use cases.
So this sounds really like some additional file, some XML file someone would maintain somewhere, like the SDK, where you just put some text-based or enum-based defaults, and you can have constructor function like, please create me one whatever default sampler and use this one. So this would shorten the source code a lot, make it more accessible and readable, especially later on, if you don't have to see about 20 values for creating a sampler, but you see, okay, this is my default sampler, something. And maybe it's not just for the special SDK, maybe we should just make a tool you can use, and you make an XML file or JSON file where you define your defaults for your engine and generate it, and then use some utility library which reads the XML file and generates the stuff for you, hopefully as source code and not at one time.
Mark, you want to say something?
I was just going to say this is a perfect opportunity for anyone to provide code to the SDK, and feel free to put in a pull request. But yeah, I mean, the whole point of us doing the SDK is to make things easier for you. And I'm not saying that we've reached it. We obviously, a lot of the samples were written as Vulkan was being developed. And so some of them aren't ideal. But if you encounter anything like a pain point that they're talking about here, let us know, and we can always add it to our list of things. We have, I don't know, 8, 10 developers, I can't think of right offhand, actively working on trying to improve the layers and other things.
I may be completely smoking something, but I was under the impression that there was a period during which, as we were designing things like enum values and structures, because Vulkan has all these huge structures you have to fill in, I thought we were consciously trying to arrange that if you B0 the struct, you would get something reasonable where you would only have to set a few of those values, and it would not be nuts.
I'm just saying swizzle.
Yeah, that is true. It's sane in the sense that if you set it to 0, it will do something. And it's not, yeah. And basically, it will probably turn everything off, so it won't crash. But yeah, so there is a sensible default from a perspective. It just might not do anything useful. I think this is kind of the reason I'm saying, though, well, I guess we're all agreeing now, that having defaults for specific use cases in some sense is probably the right way to go. By the way, this whole going back and forth and arguing about what we want is exactly how a Khronos meeting usually goes. So
you're getting a weird insight into how we spend our week.
So I just wanted to mention in the porting thing that Alon talked about, I thought the talk was really interesting, but it was clear that he missed the first slide, which was where the screen is black and you don't know why nothing's rendering. Because that's always step 0.
Well, yes, but even in GL, so it's not like we've changed
No, that's
there.
not a Vulkan thing.
Yeah.
That's a porting thing.
Yeah, I may have overcut the slides down, but my colleague Suwon gave a 4-hour version of that talk. I'm sure we can fill out a couple of days just sharing the pain from the beginning. But it is a challenge at the very beginning to get things going, but that's why we have all these resources. One additional point was in terms of what you guys need or what you think is the right things for us to provide. Khronos is primarily a standardization body, and the spec is not meant to be a user-friendly guide to use Vulkan. It's meant to be a lawyer-friendly guide, if such a thing exists. And so everything else we've been building up in these kind of events, it's good to know, have we got it right, and what else do you need, so we can hone it correctly, because the spec is not meant to be your first introduction to Vulkan. It is ours as implementers and manufacturers. Thank you, Michael. But it's not meant to be the main resources you go, but we're not so great at necessarily, I think that's a fair comment, at building up some of the additional resources. And I think it's great that, like on Luna G, you have a whole bunch of tutorials and the sample repository, but there's a lot more we need to do.
So one of the things that I think is worth noting in Vulkan, the shape that it took, is that what you're seeing now in the complexity that's exposed to the application developer is complexity that existed in all of the GL implementations. It's just that you didn't know it was there. And it is kind of fascinating to understand that in order to do things efficiently, these things were all there before, and applications didn't know, and drivers tried to guess what the application meant. And this is a much better world, even though it does mean that there will necessarily need to be some abstraction on the application side now to make it all not give you sensory overload.
So we have time for one more question. No, just kidding. That one went on for half an hour, right? So that's good, it's good. So yes, another question.
So one of the advantages of Vulkan, I see, is that it kind of simplifies cross-platform development between like PC world and a mobile. So, but what about the future of WebGL? Are you considering to kind of advance WebGL to kind of have like a Vulkan web or something like that?
Yes, so I can answer that one. So the WebGL is obviously facing an interesting point in its evolution, because the golden age of having OpenGL ES available on every platform, well, it's still here, but it's not evolving. We want the new generation of APIs to be reflected back up into WebGL. And OpenGL ES 3 is the latest on the Apple platform, so the time is now to figure out what to do. So there've actually been, there's no decisions made. I want to put a big star. But some of the interesting discussions this week have been, can we come up with what we're calling a portability API, 3D portability, where we do an analysis of the intersection of the three native APIs, DX12, Metal, and Vulkan. And is that intersection in some way a usable API surface? And if so, we could potentially kill two birds with one stone. One is to actually perhaps even standardize that API and make it available to native application developers who want such an API for portability that probably aren't using a gaming engine already, because the gaming engine, of course, will probably solve it down at the lower level. But there's definitely a broad class of application developers that might find that useful. And that API would also be liftable into JavaScript and WebAssembly, and would be the foundation potentially for a new generation of WebGL. So I'm actually really interested to know whether that kind of portability API is an interesting idea to people here. Grab another beer and come tell us afterwards if you think that's crazy talk or useful. I'm actually we're genuinely interested, because we haven't decided yet. We're just exploring what we should do in that area. Did I answer the question? Yeah.
So I will mention, just for the sake of acknowledging it, just for the sake of making noise, that I think that as performance-centric as VR is, it has been recognized within Oculus, and I think probably more broadly than that, but within Oculus that the value of web-related content, even to a platform that's super sensitive about performance and making sure that latency issues are addressed, cannot be ignored. And so APIs that allow you to express things in VR, which will necessarily include graphics, are really important. I do share, the concern that Vulkan basically lowers or reduces the thickness of the API in some really important ways, and they were very desirable, sort of choices that we made to make that layer thin. But it does now put a gap between the web and the API that you would choose, and I don't think directly connecting them together is a great idea. But then we have to figure out what should.
But there's lots of other interesting stuff. I mean, the other interesting interaction between kind of Khronos native API land and web land is web VR, which is an exploratory group at W3C. We're hopeful that the VR initiative, defining interfaces to a bunch of HMDs, trying to help fragmentation issue down at the native level, will reflect back up and help the web VR folks working in the web space too. So this model of WebGL and native space being lifted up, OpenGL being lifted up to WebGL, this portability API potentially being lifted up, the VR initiative being lifted up into JavaScript, I think is a kind of a proven model that hopefully we can continue. Okay, any other questions? Yep.
I have a quick question about the Vainglory port. You mentioned that there was a significant memory reduction in the Vainglory version, and I was wondering, where is that coming from? Is that just a difference in texture compression, or should we expect less memory use with Vulkan?
So I think, what I was saying was that we need to actually start subdividing up all the changes we've made. So because a lot of it is due to moving it from ETC1 to ASTC. But I think there are other examples where you can reduce memory use by having more control for when, because it's up to you when you free resources. So you are managing your object, you're managing how much memory is used. So there are benefits there as well, but with Vainglory in particular, we haven't subdivided how much of that is due to Vulkan versus ASTC yet.
The other obvious place to look for memory saving is from the fact that you can alias memory resources. So if you have textures used in different parts of the pipe, depending on the architecture, you may be able to recycle that memory. But that is heavily, a simple pipeline, you're not going to get any of that saving because of the pipelining. It will never be safe to reuse it for other things.
Also, the OpenGL drivers have to do a good guess about suballocation, which you have to do on Vulkan on your own. So if you're allocating an object with 32 bytes, it's possible that the driver says, yeah, my allocation granularity is like 512 bytes or 1 kilobyte at least, and you get way bigger chunks. And in Vulkan, you can say, okay, I want to have 32-bit byte alignment for my objects, and you suballocate 1 or 2 kilobyte of memory, which is most of the time still way too small, but you could. And then you can pack densely your objects. And you can also have one pool for all objects which are dynamic and throw it away at the end of the frame to prevent fragmentation. In OpenGL, the driver has to guess, okay, those objects might belong together or not. And then you have one big block, one small block, a big block, another small block, and you're freeing the big block, and you still have the full memory occupied between the two small blocks on the GPU side. And if you have to allocate a slightly smaller block, you can't use a block in between, and you allocate a new memory resource. And all the stuff you can control under Vulkan, but you can't control under OpenGL. So this is one of the reasons why you can also save a lot of memory if you are careful.
Another thing, too, that we kind of glossed over in the tutorial presentation is that a lot of the Vulkan create and destroy commands, actually, you can pass your own allocator into. And so you control a lot of where that memory comes from. If you want to do, like, anything that's, created once as a heap, in another case as, like, some kind of memory pool, you have a lot of control over that if you want. And historically, that's happened behind the scenes in your OpenGL driver. So you can kind of, if nothing else, you can kind of keep track of what's going on whenever you call create device or create text or, pool or whatever. A lot of that information is now out there for you to see. And you can see, okay, hey, I'm using a lot of memory whenever I create this, command pool, and so I really need to, restrict how many command buffers I can allocate out of each pool, or, along those lines. So the information is there, you just have to look for it.
Although I would stress that the allocator callbacks are primarily for, like Mark says, they're for development time, kind of looking to see where memory is being allocated, but don't think that the allocators passed into functions are so you can do a better job of allocation. Because
Michael, I was going to say, we have at least one driver developer on the panel here, so it would be good to get a sense of, between OpenGL ES and Vulkan, what is the memory profile of the driver look like? How much do you own in one versus the other? Is it significantly different?
So I think potentially in Vulkan you allocate more memory, but that's a good thing. So in GL, we have to optimize for the smallest case because, so OpenGL drivers, this isn't true for, but there are other APIs that we implement where if you allocate more than a certain amount of memory for a single triangle test, you fail that test, which is great if you're writing a single triangle application, but I assume most of you are going to be drawing more than one triangle. So you don't care that my driver is optimized for a certain amount of memory that fits under the one triangle limit. So in Vulkan, it's great because we don't have to guess. This is what I was talking about with command buffers. If you draw 10,000 draw calls, or 20,000 draw calls, or 30,000 draw calls, or 300,000 draw calls to a command buffer, we will duly allocate the exact amount of memory that you require modulo some allocation granularity, which is very small compared to OpenGLES. But in OpenGLES, it's much, much more difficult to do that. We can't ever possibly say that we're going to be allocating enough for 30,000 draw calls because other applications might only use 30 draw calls. And as a driver, we have to optimize for every single application at the same time. So Vulkan uses exactly as much memory as you want us to use, which means for any given usage set, we use significantly less than GLES. So in terms of memory footprint, given the fact that memory allocation is so forced onto the application, and like Marcus was saying, that's really important, that granularity of memory allocation is now completely down to the application. And again, before the driver had to guess, we had to guess, are you using 32 bytes, are you using 64 bytes, are you using more, or are you using less? But now that's your responsibility, which is great. And it sounds painful for you guys, but it's not, because you have a lot higher level knowledge of exactly what you're using that memory for compared to a driver. So in answer to Cass's question,
What was the question? The question was answered a long time ago.
Yeah, but this is Khronos.
Why did it use less?
So no, implementations don't use less memory in Vulkan, but we use the correct amount of memory.
Well, the one, I guess it depends which question you're asking, what the details of your question are, but I'll just say a thing and we'll decide whether it applies or not. So one thing that I mentioned earlier that I think someone in the audience asked was about does the driver create extra copies of buffers and stuff for you? So I've seen a few apps over the years which do this thing where they go, draw, update the one vertex buffer I'm using, draw, update the one vertex buffer I'm using, draw, update the one vertex buffer, over and over again, like hundreds of draw calls. When you do that, the driver has two choices. It either stalls and waits for your draw to complete and then creates awful, awful lack of overlap and massive stalls, or it copies that data somewhere, which means allocating memory to store that data somewhere. And in the worst case, that could mean copying your entire buffer somewhere, which means that for every draw call, you've got an extra copy of a vertex buffer. Whether you call that application or driver allocation, doesn't matter. You would now see that if you try and do that in Vulkan, because you're going to have to try and allocate those yourself, at which point it should be pretty obvious you're doing the wrong thing, which should hopefully lead people down the right path.
And I think that's another example similar to the ordering one from the slide deck I gave. Of at first you will have more pain, but once you get it right with Vulkan, you'll be able to optimize a lot more. So I think then that's what the memory allocation conundrum and difficulty is one we hope that there'll be community contribution on and realization that we need to actually have some common open source resources, because it is really needed by developers.
And for my memory, I assume Cass was also asking for CPU memory, maybe. Yeah, in Vulkan the objects are very slim, and usually we don't have to do, well, I think we actually don't have to do any heuristics, so we don't need any additional memory for storing the heuristics, computing them, or some stuff like the whole vertex attribute set on OpenGL, which was quite huge, and you might have to store it, and if you're creating vertex array objects, you have the full state in this object, and you're changing, and you don't know which values are required. And most of those inefficiencies are gone in Vulkan, which is quite nice. But with regards to suballocation, there's maybe one new pain point. So for now, the driver knows more or less how many allocations you are allowed to do on the operating system. So if you have a GPU with a lot of memory, the driver knows, okay, suballocations have to work on extremely large pages. And if you're writing your game and you assume, okay, I want to create 4 megabyte pages for whatever reason, and you're starting to allocate and allocate and allocate, it might happen that you run quite fast out of operating system resources, and your application will fail if you have used 1 gigabyte of memory. So this is a pain point, which is a little bit hard because the operating system doesn't tell you how much you're allowed to allocate. So in general, try to use allocations as big as possible, allocate upfront and do your sub-allocations, and so don't do small ones.
How big would you say a good VK device memory allocation would be?
It depends on the size of the memory, but under Windows, if you are lucky, you can get about 1,000 or 2,000 allocations. If you're lucky, not always. So sometimes you get only 200, 300 allocations. And so you really have to think about what you're doing.
So we're talking about 64 meg, 128 meg per device memory allocation?
Yeah, stuff like that.
Yeah, that sounds reasonable.
So we have boards with 24 gigabytes of memory.
Yeah, there's a question. No, sorry, we'll come right back to you. He's been very patient.
So I'll ask a question actually about memory. So in DX12, you have to manually worry about, copying stuff back out of VRAM or dropping it from VRAM and putting it back, or at least evicting, so you hint to the driver that it can move things out. What's the story in Vulkan? Is that something we have to do? Is that something that's just handled automatically but then might have performance issues?
So it's something that we are aware of, and we may or may not have a timescale for, and I will not tell you what that timescale is.
Since this only affects Windows, people looking at Windows are thinking about it, basically, is what we'll say.
Yeah, so basically you have to take care of managing your VRAM, and especially on Windows 10, you are limited with regards to the total amount you are able to use. And this also might change while your application is running if you're getting moved to the background. And this is a real pain point you have to take care of. And we don't have any API in Vulkan yet.
No, at the moment it's just a case of the driver will figure it out, which is the same as it was in GL. And I think that was sort of, we looked at it in the early days as and the people who were involved were basically like, it's probably not a big deal, and then they're not so sure.
In the end, the driver can't take care. So Windows might decide to move your application to a lower priority if you use too much memory. But if you're a game which is running full screen, usually it shouldn't be a problem.
The takeaway point from this is we are not unaware of these problems. We are not completely ignoring them.
But if you do have a problem, please raise it on GitHub, even if it's just this is hard, and if it's because we are missing a feature or because you think you need some example code, whatever the heck it may be, put it on GitHub because we'll look at it.
Yeah, so, I mean, we're not using Vulkan yet, so I have no idea if it'd be a problem. Maybe it just works and it's great. But yeah, I guess just thinking about DX12, they did it for some reason. Maybe it's good, maybe it's a bad reason, but yeah, potentially it's something that might be of a concern.
Yeah, and it really is. It's to do with the way Windows manages memory more than anything else. So DX12 being purely a Microsoft thing, it makes perfect sense for them to have it there. Portable API we weren't really sure what to do with it.
So follow-up question on the memory then. Like in Windows or in DirectX 12, you basically have a resource descriptor limit, which is very hard, and switching descriptor heaps is problematic. Are there similar limits in Vulkan? Like if you have 1 million texture descriptors,
if you have 1 million texture descriptors, I would be very impressed with how small your textures are that you can fit them in VRAM.
Yeah, so but like they're shared between vertex buffers, index buffers, texture descriptors, different samplers, sampler descriptors. We're running out,
You're
right?
specifically talking about the number of descriptor handles you can create to put into a descriptor.
Yeah, so generally speaking, if you multi-frame it and you divide that number by however many.
I think there might be some limits in Vulkan, but I don't expect them to be tiny. It might be the Windows implementations have a lower one, I suppose, but I mean, they do map to some degree, so.
Yeah, so I guess this is true of DX12 as much as it's true of Vulkan. Certainly, I think we have some material out there which is advising don't allocate buffers per buffer, allocate a single giant buffer and then subdivide it and use offsets, because then you don't pay a descriptor per offset, you're just paying a descriptor per buffer. Image arrays can help with images, samplers less so, but again, there tends to be fewer samplers. So I don't think that's a Vulkan-specific problem, and I don't think Vulkan is aiming to fix that in any way that DX12 hasn't.
Yeah, I think in general the rule is sub-allocate all the things. If you're allocating all the things at the top level, you're doing it wrong. As few memory allocations as you need. Like we talked about like memory allocations earlier, you should have ideally one allocation per type that you need, and that's it. And it should be one big and you should sub-allocate. And the same is true for buffers and images too.
Yeah, the problem with that kicks in if Windows 10 decides you now own less memory, you need to kick a pool of 1 gigabyte.
Sorry, you're saying you need 1 gigabyte for your giant buffer?
Like if you say allocate per resource type, then you have really large pools, and then when the video driver tells you you don't have the memory, you're going to kick large quantities.
Yeah, no, so that's very interesting, and I think it's where kind of the more modern sparse APIs come into effect, where you can allocate a 2,000 big image array and only back the images that you actually require. And it becomes interesting how you do your memory management, because you can start doing really interesting techniques, especially how Vulkan separates the resources from the backing memory. You can start shuffling memory around using the sparse APIs, and that's also true of buffers as well. So yeah, yes, your virtual allocations become very large, but your actual memory usage can become significantly smaller.
Okay, there's a question here.
I have a general question. From an SDK point of view, your main customer is games. I would say Valve is driving a lot of the development. What other applications do you see Vulkan being a first-class citizen other than gaming? Could it be in other products like compute vision, or could it be in the web? What's your feeling?
Well, one of the things that I'd kind of like to see is some scientific visualization applications. You can imagine a supercomputer someplace who's running algorithms that are already inherently parallel, and they'll be generating massive amounts of graphics, and then that type of threaded solution might map very well into a Vulkan renderer.
So I can say the professional market for visualization hasn't yet started to use Vulkan, at least the ones I'm aware of. So currently it's mostly games. And for compute, I think Vulkan is interesting for compute. We will see if it's good enough in comparison to other stuff. Now, I assume depending on the task you want to do, so if you're gaming, you're wanting to do compute, the Vulkan compute is most likely more than capable of doing everything you want to do. Yeah, and Michael wants to say.
No, me next.
No, I was going to ask you a question.
No, me next.
No,
sorry.
No.
Michael needs the microphone taken away. So I was just going to mention that because my focus is mobile, I think that the application class that's most immediately benefited is games and anything that's high-performance graphics. But it is important to note that anything that runs for a long time consumes a finite battery resource. And so over time, the desire to reduce that heating and reduce and extend the lifespan of watching a movie or whatever, those are all things that are naturally going to prefer Vulkan over any other API. Or anything that efficient, I should say. But it is the efficiency gain, and it's really important in mobile.
Yeah, and there are examples we're seeing in terms of UI and other non-intense graphics usage that you think you'd be surprised, but hey, they moved to Vulkan because they're getting massive power efficiency saving from it. I think the one thing we discussed quite publicly in terms of the priorities for Vulkan was to make sure we have something for the gaming market. So there's discussions about what other needs there are, but that was a primary focus of Vulkan 1.0. The interesting thing for me in terms of compute and mobile is that the primary use case is served. The question is how much more do we need advanced compute and mobile, and then is Vulkan the right API for that? So that I think is currently an open question, which Tobias is going to answer for us.
Answer? It's a bloody tall order. Thanks for that, Alan. No, so there are compute use cases, and we are talking about them as well as other use cases because we do, have a market to serve and several markets to serve, in some sense. Specifically with compute, I mean, we're looking at various techniques, and various people, smarter people, have been looking at this sort of thing. And if you look at something like a modern version of OpenCL or CUDA, you've got like pointers and stuff. But we're kind of, some of us are against the idea of adding pointers, for instance. That doesn't mean to say we don't want to enable the actual use case. So one of the things we've been looking at is data structures and dereferencing, for instance. And I think people are starting to settle on the way to do that in Vulkan today is that you would allocate a large sparse buffer, and instead of using arbitrary pointers, you use offsets into that buffer, for instance. And that lets you jump around anywhere within that buffer, and that's all doable today within Vulkan. The question is there anything to be gained from going further? And that's the sort of analysis we tend to do in the day-to-day is, what can we enable and how can we enable it in the most efficient way possible? Whereas if you look at something, well, like OpenCL, it's like, well, we need to enable these people to do it as quick as we can. Not without an eye to efficiency, but because Vulkan's targeting, real-time, very quick and efficient computation in a very short amount of time. You've got to get millions of pixels onto the screen in a very small amount of time. Then there's a different focus there. So we have to decide, we have to make trade-offs, basically.
Thank you.
I would add a couple of things. I think I agree with Marcus that the professional guys move slower than the gaming guys, so yeah, it's going to come. But there is interest there because in many cases there are large data sets and multi-threading is going to help. And I think that, to Kaz's point, mobile offload to GPU is such a low-hanging fruit. And my example of really the Silicon community kind of failed the developer community in recent history for interesting use cases that should have been GPU offloaded is Pokemon Go, right? Wildly successful game, wonderful game, no criticism on Pokemon Go, but all the power users knew to turn AR off, and at least partially because all of that vision processing was being done on the CPU and it would drain your battery, something terrible. And that's a shame, because that was an opportunity to get more advanced use cases more widely used, and we really haven't enabled the developer community to do vision and soon neural net inferencing offload in a sensible way. And I'm hopeful Vulkan will enable that kind of use case. Any more questions? Yeah, go ahead.
So it wasn't clear from presentation, maybe I just missed the point. So does Vulkan support multi-GPU? So basically, if I detect that, I have discrete GPU and I have a, let's say, Intel comes with embedded one. So can, as a game developer, we would like to use all, power which is available.
I
and
think what we have to say is we're very aware of the problem. Actually, we did get up on stage at SIGGRAPH last year and say multi-GPUs on the roadmap.
Say a little bit more. These people have come.
Okay, well, come to GDC.
The one thing that I would add is that we do have the concept of multiple GPUs in Vulkan, which
is
neglected.
Technically true, right? You can ask your instance, enumerate the GPUs for me, and it might say you have 2.
Yeah.
And they happen to be identical. What you can't do is have them both render to the same surface. You
Yeah.
can't share anything between them.
Yes.
But can I create two instances, and let's say one GPU will use just for rendering and another just for compute?
You can do that within one instance.
You can do that within an instance. The problem is that you would have to manually in the CPU move buffers back and forth if you want to share data today.
Okay, so this one is possible because
So what we would need to add hypothetically to Vulkan is the ability to sort of make those memory objects importable and exportable between separate physical devices, or between hypothetically Vulkan application and other applications running other APIs.
If anyone wants to talk to us more about this,
Yeah.
then there are ways in, like we talked about the Vulkan Advisory Panel. If you feel like you have valuable feedback on that, that's the sort of thing we're interested in for the Vulkan Advisory Panel. And I think Neil mentioned we're going to have a face-to-face meeting at GDC. So if anyone's
you're running into the limits of, as I said, we want to be responsive and we want to be transparent, and we have also a very strict NDA on future technology that hasn't been ratified by our board yet, and that's because of the lawyers. And we don't like operating that way, but we have to. But
there are ways to sign an NDA with us.
Right,
but it's going to be solved very soon, I think.
It's a problem we're very aware of.
Khronos president on record. There you go. Yeah. But yeah, you can do some stuff today. It sort of depends on your use case in a very technical sense. If you've got 2 GPUs and 2 displays and they're hooked up to one each, then you can do that. If you plan to just stream out to your CPU, you can do that without too much hassle. You could even share by coming back to the CPU in some sense without too much hassle, just extra copies, but no synchronization cost necessarily. But
you still couldn't do 2-display stereo because you wouldn't be able to synchronize the 2 GPUs.
Correct.
Because you can't share semaphores.
Yes. So there are holes. There's some stuff you can do, some stuff you can't.
Okay, you really do have time for one more. Yes, go ahead.
Hi. So from listening to various things said today, obviously synchronization seems to be one of the pain points. And I'm quite interested in the debug layers. The debug layers like the threaded one, for example, does it actually check synchronization?
So we're continually trying to improve, especially around synchronization. We do some validation, especially around the various barriers and fences and semaphores. But it definitely is one of the areas that we're continuing to work on. As I said, that when you even look at our original samples, that they kind of lag exactly what the best case requirements are, because we developed them as the spec was being developed. So yes, it's an area we can continue to improve on.
I would say that I think my personal crusade somehow has turned into making synchronization language better. Vulkan sort of inherited a lot from GL in many ways, including the lack of a well-defined execution and memory model. And so I went through, some community members pointed out that they couldn't figure out how our synchronization stuff worked because it was pretty patchy at best in terms of specification. I subsequently went through and took a couple months. It was a pain in the ass, but I, along with some other of the working group members, basically went and redefined the synchronization chapter, and that work is still ongoing. It's now in a usable state for the most part, but it's not all there. You can kind of figure it out. And because it's been a little poorly defined, these guys have had a hell of a job validating anything. I'm actually amazed they've got what they've got. And we're certainly looking to improve it over time. I think it's getting to be in a good shape, and now that they've got something meaty that they can dig into, I'm hoping it seems to be improving rapidly anyway, but that can only get better over time.
So you mentioned the threading layer and the validation layers. Did you do that? Mention the threading layer?
Yes.
Yeah. So what in the Vulkan spec, it specifies there's a lot of objects that you have to guarantee your own synchronization on the host side. And so the threading layer does that. So it's meant to keep like two threads from accessing the same object. So that's one type of synchronization. And then there's the other part that Mark and Tobias talked about, which is the queues, fences, and semaphores, and having the validation layers do explicit checks for those. And those are in place too, as we said, but we're continually improving them.
Another thing that Tobias has kind of talked on before too is that there's this idea that we could eventually do a performance layer that's a lot of it is tied towards making sure you all properly synchronize, because that is, again, it's probably one of the biggest pain points we see. And I mean, Tobias kind of glossed over how much he rewrote the memory management stuff and the synchronization, but he did a phenomenal job.
Yeah, and I think too another role that this performance layer might play is, we talked a few minutes ago about make one big allocation instead of a bunch of hundreds or thousands of them, and you could imagine this type of layer. It's not just performance, but it's also looking for bad Vulkan practice. And so it would, I don't know what the limit is, but it would say something like, oh, if you make more than say 256 allocations in some period of time, it would give you a warning and say, do you really want to do that? So you should make one big allocation.
So I think, ignoring Vulkan for a second, yeah, synchronization in Vulkan is difficult, but at the same time, learning the Vulkan synchronization model is not just a sunk cost into Vulkan. That synchronization model is true across all of the other modern APIs, but also possibly as importantly across kind of GL and GLES. So you can do a whole bunch of stuff in GL and GLES today, and it works, and it sucks, and you have no way of knowing it's sucking. So spending the time to kind of learn the Vulkan synchronization model where you're forced to do it properly will absolutely benefit you in all of your other API usages.
Yeah, I think it came as no surprise that a massively parallel heterogeneous system with complex caches and hierarchies wound up being complex on the synchronization side.
Yeah, and I just channeling Tom with what he kind of calls a meta point. So as we're nearing the end, I think both on all the debug and validation layers that currently exist, but also adding additional layers. This is the hope of fostering a community that we've been trying to do. So if you spot something that the validation layer doesn't pick up, feel free to put in a pull request or ping the LunaG guys. Similarly with our conformance tests, if there's a particular, your vendor of choice that is disobeying something, suggest a conformance test where the spec catches them out. So we do, yes. So please do engage with us, and if you think there's anything more that we can do in that front, suggest it.
Just one real quick thing. I think you've seen through it that the real reason we created Vulkan is job security for you all.
And on that excellent point, we must finish. So please remember to fill out your evaluation forms. We are genuinely interested in what you thought. Please be honest. And a few thank yous. So Karen at the back, thank you for organizing everything. And thank you to all the panelists. You guys have been awesome. Thank you for taking the time. You had to slum it in Vancouver for a weekend. No, it's been awesome to be here. So thank you, guys. And last but not least, thank you for everyone here. Thank you for your time. Thank you for spending the day with us. Hopefully it was useful. We'd love to get your feedback. Thanks for coming.